when we are discussing, Dr. Agarwal was pointing it out about about the the hazard calculation, and he has mentioned that it can be done in a two-way. One is a deterministic seismic hazard analysis, and other is the probabilistic seismic hazard analysis. So this seismic hazard therefore can be done in a two ways. Okay, so one part will be the deterministic way, and other part is the probabilistic way. Right now, in current approach, we are mostly doing the probabilistic as a probabilistic seismic hazard, but deterministic seismic hazard I will touch upon, because that might be very simple things to do, but there are obviously a lot of issues and lot of fallacy might come in if you use the DSHA. In compared to the DSHA, might be the PSHA is much more elegant and much more taking care of all the factors of the fault ruptures, the magnitude possibilities in a much more better way. In the better way means in a probabilistic way, right? So that's the main emphasis. Now, before I do that, I like to tell you that seismic hazard map are usually provided into a percentage of exceedance, right? All the values are given as a percentage of exceedance in few years, right? Say suppose 10% of exceedance in 50 years. So that means, say suppose at any point the PGA is 0.01. Now that has said that this is the 10% probability of exceedance of PGA in 50 years is 0.01, right? So that means what? That means it is basically calculated like this, say, so let's see that 10%. So it is a 10% probability of exceedance, exceedance in 50 years. In 50 years, right? So these things will be like this, right? So therefore the lambda, which is the probability of exceedance values, will be equals to minus, okay, this is your log 1 minus of P, okay, divided by the time. So that's the part, right? So if you have see that, so P will be equals to the 10%. So 10% means 0.1, and in 50 years, in 50 years, so time equals to 50 years, right? So then your lambda value will be coming at equals to how much? Minus of log of 1 minus P. So 1 minus 0.1, okay, divided by T is 50 years. Can somebody calculate this number? What will be this value? It's a natural log.
0.002. And so lambda equals to 0.002.
So T, if we can say it's a return period, so the return period, so this return period will be equals to 1 by lambda. So that will be equals to,
so how much? It's not experience. And the things like in this means like straight that what the continuing supply in the map. Right? Swinging possibilities. Finally, crispy. Sorry, finally. Look, this is not 0.002. It is the 0.0021 something. 7,000. Right, 0 1 just to 1. Being 1. 1 to 1, right? It's me. Right. And it's 470 notes all down. Yeah, 476. So lambda comes out as a
476 years. Okay, so 476 years. So if it is a 10% probability of exceedance in 50 years, that means, so let's say suppose the peak ground acceleration at some places is given as a 0.1 g. Okay, say let's see the 0.1 g with 10% probability of exceedance in 50 years. That means that 0.1 g can be exceeded at that site in 475 years, right? So that's the thing. So 10% probability of exceedance in 50 years mean. Okay, so in general, our probabilistic seismic hazard analysis, they all give the numbers at a particular site based on this. Okay, this is, or in some of the very critical structures, which are basically say hospital, might be the school buildings, which are very critical structure, the probabilistic seismic hazard of that structure, we always prepare it with a 2% probability of exceedance in 50 years. 2% probability of exceedance in 50 years. So that is their exceedance in 50 years. Can you calculate what is their return period? 2% probability of exceedance in 50 years.
Good BTS. All right. BTS will be 0.1. Well, BTS can be any number, so that I do not care. But the question is 2% probability of exceedance in 50 years means what? In Sweden, 8.0 words. Good. 0.002. So that means it is how much? That is right. No, this is a little bit, there is another number, 0.004. 247, right? So, 2478, 2475, right? So that's TR comes out to be 2475 years.
So you can understand that that particular sites or that particular things, basically the the construction has to be made in such a manner so that that value will not be exceeded in 2000 years. So that means it will be much more strict type of constructions, right? So that will be this one. So you said this will be 0.004, right? 0.004 something. So, so 4 into 10 to the power minus 3, right?
2475 years. Yeah. 2475 years. Or the lambda value equals to 0.004 something, right? So, it's an approximate value. 103 was for like 445. 0.00%. Awesome. Here, wait. So 0.00 or 6, 446. That's the number. Which this lambda, right?
So this will be equals to 3 into 4.46, right? So 10 to the power 4.46. So let's see, 10 to the power minus 3. So 4 will be something like this, right? So if you go there, so that will be the value for this curve, whatever I have generated last time with your 2 at a particular site, right? So this is your corresponding to 0.446, and then you get down to your this number. So that will be the G value. If it is a G or spectral acceleration, then this will be the number for that particular site. So what we will be doing is basically for all the sites or all
triple zero or double zero. That hurts. That worse. I don't know. Dollars.
So you talking about you get to the nesting cook and then say if it's so.
No, I'm not really. You guys are doing so.
I did one second. So
Then I'd have to check. Nah.
yeah, it's two sides.
What thing? When customer thing since we didn't take it's understand the food.
Say it.
With me, this thing so good here told me to policy and keep playing.
It's just like another 2,500 years if I move it 0.2, that is single.
What?
If we take 0.0004, then it's 1 by reciprocal, and that's reciprocal is number 2,500 years. Right. And if we go by the exponential progression, then here we will get 1.75.
I think, okay, Mr. Trap wants and then I think it's really small. Still, but it's related to change. Looking at the necessity on where you see takes a ball with you. But then when they said, what? Motivation. English, my everything's he was supposed to be, he doesn't be enjoying it. Was interesting. Yes. When you sleep to the church.
Do I know? We sure kiss.
It's Disney. 0.000446, right? Okay, so the 0.000446 ends. What? So 0.1.
0.00446, right? So that means this will be the 4 point. So that means this will be here, not here. Let me see. Okay, so this is 2, 3, 4. So this will be the point, this number. So we can say this is your spectral acceleration at this point, right?
Sorry, the return rate of building is more than this nearly 10 years. So why we are making like much of years the return rate? No, that's not the case. The case is this, that
one is the lifespan of a building, and this is the probability of the building to survive, right? So this is a lifespan. The building can go within 100 years, so that's fine. But if there is an earthquake happens, that building will be intact. That is basically we have to decide. The building can go. Building may not be the health-wise. The building can not survive more than 100 years. But if there is an earthquake happens, then what I am saying that this building has to be constructed in such a manner so that this spectral acceleration of 1 second might be this value, which will be equals to 0.03 or something like that, this much of second. This should be the spectral acceleration of the building. So that's what the building has to be constructed so that it has a return period. It can withstand any earthquake which has this much of exceedance, right? So that is what the building construction thinks. That's a completely different with the building lifespan, right? Lifespan is a different thing. The probability of exceedance is a different calculation.
It depends on the probability of exceedance. Suppose if we take 5%, as a year may change 10%, but yeah, can you? So all the things. So suppose the roads are constructed
In a different ways. Say the roads are constructed in 10% probability of in the 75 years. So they all make a different decision. That the decision indicate what should be the spectral acceleration we need to fix for the design. Okay, so that will be the decision on the design level. That much of earthquake it can withstand. Okay, at a 1 second. So that means at a 1 second it will withstand 0.03 G, which corresponding to the 10% probability of exceedance in 50 years. Okay, so so that's the part which we are interested, but that is what we will be trying to calculate a return period or number of exceedance. Lambda is the number of exceedance per year. Okay, so lambda is the number of exceedance per year. So 1 by lambda is equals to a return period. Does it make sense? So lambda means it's a number of exceedance per year. So okay, so yes. Now what I was trying to tell you is this, that this is what we were doing yesterday for a particular fault at a particular site with a 10-kilometer distance, and then we have calculated what will be the spectral acceleration. Say suppose the predicted acceleration is 0.717 G, and we try to calculate what will be the lambda value, right? So so I have been given the G value. I have calculated the lambda, okay, and that lambda I had plotted it here, right? So given the G or that particular area based on the Bourgeois model with this much of distance, this is the attenuation money relation. It's the Bourgeois attenuation, Bourge-Fumel and Joyner attenuation money relation we had used. BFG attenuation money relation we have used for 10-kilometer distance. We have calculated that for this fault, the G value, the predicted G value will be equals to this one, right? So that's what we have calculated for that site. Okay, and we said that the logarithmic standard depression is this one also, and overall lambda point is 0.01. So that is your this calculation. So then we calculated what is the probability of at 1 hertz, at 1 second, the spectral acceleration at this rate will exceed 0.5 G, right? So that is what we were trying to calculate, right? And then we said that if that is the case, then this will be coming as a 0.0191, the probability of exceedance with this 0.05 things, and that is what we got. So the annual rate of exceedance, we can calculate with this probability value multiplied with a 0.01, right? So that is your annual rate of exceedance. So the per year, this will be the exceedance values. Okay, now that's fine, but that is calculated at the rate of lambda equals to 0.01 rate, right? So we said this one, so we have plotted it, this number at a 0.5 g, right? So this number at a 0.5 g, this value is like this. And similarly, we had plotted it for the 1 second at a 0.2 g at the same rate will be equals to this. So these are all calculated with your lambda equals to 0.01 or lambda 10 to the power minus 2, right, with this lambda rate. Now annual exceedance rate for this one is equals to calculated with this one will be equals to 0.001191. So that will be this one. So for this one, for 0.2 g, this will be like this. But what I want, so this is for one particular site. I do it for the another site, and I got the same type of pictures like this with a different number. Now, what I do a uniform probability distribution map. So this earthquake hazard map, you will be seeing it's a uniform probability. Now, here at a 0.01, the probability is, the annual rate of exceedance is this. 0.2, the annual exceedance rate is this much. So instead of doing that, what we do is this, that we give a uniform probability of exceedance. So that uniform probability of exceedance is basically, say suppose 0.0046, right? So that's the uniform probability of exceedance, and that we give from this curve, calculate from this curve, and then compute that this will be the spectral acceleration. So now in a map, we said that all the sites I have given the 0.00446 as their base, and then only give that, okay, this much, this site will have a 0.03, this side will have a 0.05, and this one, and these are contoured so that with the same uniform probability of 0.000446, that means the 2% probability of 50 years, I have given for the different side different spectral acceleration values, right? So that is your spectral hazard map of the region. So that means what we call it as a uniform hazard spectra. Uniform hazard spectra means we had make it a uniform. We are not giving different site, different exceedance values at different rate. We are just giving one exceedance rate, but the whatever the different sites, the acceleration value is, that we are calculating, right? So here we are calculating for a 0.05 z, what is this number? That is what we are calculating, okay? Or might be 0.02, then what is that number I am calculating? But instead, we are calculating, we are giving a constant lambda, and then we are saying that if that is the lambda, then what will be your exceedance values? So that means that might be someplace 0.5, someplace might be 0.2, someplace might be 0.01. So that's we are trying to assign. Does it make sense? So what is your probability of exceedance map in your, if you see a probability of exceedance map, you understand that that will be always uniform probability. So that means all the sites are being pictured as a uniform probability values. Does it make sense? It might be that each fault has a different things, but that's okay. But we are trying to calculate all the things. It might exceed different values, but we are saying that, okay, if it is a 0.000446, then what will be the values? So that is what we are contouring. Okay, so that means if it is a big number, that means that that site has a much more potential to get damaged within the say suppose 2500 years or something like that, 450 years or 500 years. Is this the basic things clear? Okay, if this is clear, then we can go ahead. Otherwise, everything gets confused with the probability model, because the probability things are a little bit like this. So if you do not understand properly, then it will be all messed up. Okay, so let's see. Say suppose these are the two ruptures. That means two places, right? So two places, two different fault has a two different ruptures at this one, right? So this is the two different fault things. But if I wish to have a uniform, so they are following different hazard curves. But whenever I am trying to do, I will be always take the 0.0046 and try to draw this line, because that's a 2500 years probability of accidents or 2% probability of accidents in 50 years. And then for this fault, I draw this number, this fault, I draw this number and read these two values. So although these are the two different places, I am saying that, okay, with the 2% probability of accidents in 50 years, this side will have a spectral acceleration this much, this side has a spectral acceleration this much, right? And that is what we will be doing all the contours for the different places. So these are the different hazard curve for the different places. That should be. But when we are doing it, we are cutting the same spectral hazard level and then draw these numbers so that we can show that which level is a more. So definitely this has a less hazard than this side, right? So that means this side will have a more hazard than this side, means more spectral acceleration for the 2% probability of accidents, right? So that is what we were. Yeah. The faults are different means that is basically depends on the particular site. Yeah, basically the faults, the contribution of the fault on that particular site, right? So that's because ultimately we are living on the site, so we are trying to calculate at that site, that fault will have that much of probability of accidents. As I said, that the probability calculations are two types. One is the DHSA and DSHA. DSHA. So DSHA, deterministic seismic hazard analysis. So at this site, we say that, okay, what is the deterministic? So that means if you know that this site will have a 6.5 magnitude earthquake, this fault can produce, and might be at a distance of 50 kilometers. I calculate what will be its ground motions, or that means either the spectral acceleration or the PGA or these things. We can use it from the attenuation model, and that's their probability values. Okay, so that is what it's only one fault, one number, one magnitude, one distance, and calculate it. Okay, so that's your totally determined. So that means you know this is the value of the distance, this is the value of the magnitude, and use that money relation with the attenuation money relation and compute its possibility of exceedance, right? So that is your totally deterministic values. But that is okay if you know these things, but it is not okay because we do not know actually what part of the fault will rupture, what magnitude will produce. These are all uncertain things. So DHSA will not account for that. So DHSA can only account for a particular magnitude at a particular distance and compute these values. Okay, so for that, for calculating the DHSA, we need to first identify and characterize the earthquake sources around the site. So first you need to do that. Second, we need to find out what is the source to site distances. So select those source to site distances, and then calculate the ground motion based on any attenuation relation. Let us see the Bourgeois method, or where you give the magnitude, give the distance, and calculate the PGA or the SA values, just like as we have done it last time in your. So that is what we can call it as a ground motion attenuation relation, or ground motion prediction equation. Ground motion prediction equation, GMPE or GMM, ground motion model and ground motion prediction equation. We put that magnitude, we put that distance, we put that VS30 of the site, we put all the numbers, and it will give you a ground motion site of interest, and that you can identify. And if that particular site is surrounded by different fault, having different magnitude, then you calculate for all the faults, all the magnitude possibilities, and then find out which one is the most or the largest one. So then that will be the controlling factor. So we will be constructed our buildings or house based on that. So this is your DSHA main theme. Okay, so we select the earthquake source, we select the distances or find out the distances of the source, we found out the ground motion model, calculate the things, and then assign from there which one is the largest. That will be the DSHA value, right? It is as simple as that. So that, say suppose this is the site, so this is the site, so this site is located with this much of distance, might be this site is this much of distance. Say suppose this fault has a, so there are, one is the line fault, one is the, so this can be created M3 magnitude earthquake, this can create an M1 magnitude earthquake, and this might be the M2 magnitude earthquake. And so every distances are, all the distances we have calculated from here, from the source, and compute these values, and compute the different intensity measure. Say if you want the PGA, if you want the PGV, then PGV. If you want the peak ground displacement, peak ground velocity, peak ground acceleration. So these are the different IM values for different magnitude. We calculate how much with the distance, how it is being changes, and compute that values. Right? So it is as simple as that. So let's see a example like this one. Let us take an example that if it is a site, so this site, at this site, there are 3 source zones, 1, 2, and 3, right? So 3 source zone, 1 is source number 2, this is the source number 1, it is a line source, this is the area source, and might be this is your a point source, right? So these are the different sources present, and these sources has this much of distances are all given. First source will have a 23.7 kilometer. Second source will have a 25 kilometer. Third source will have a 60 kilometer. So these are all given, right? So these values are given, and this value you know. So do that, and I use a ground motion model equation which says that mu, or the mean value of log normal PGA, so that peak ground acceleration, so that is your mean value. So this is your one ground motion prediction equation. So it is called Campbell's ground motion prediction value. So it is not that the Campbell's things are very great or very interesting or very accurate. It is not like that. I give the Campbell's equation because it is simple to calculate. So that's why I have given it. So you can choose any ground motion relation that you are interested in, or do you have any argument of one ground motion relation with respect to the other. If you can do that, that's fine. So we know the distances, we know the magnitude released by each one. So this is your maximum magnitude. We all know that. Okay, so that we can put, and we can calculate for the source 1, source 2, source 3. These are the three magnitudes: 6.3, 6.7, and the 5.0. So this is what basically all the magnitude values. The distance value is already given, and so magnitude and distance, if you know, you can calculate it mu ln PGA, so that PGA value is equals to here, right? So that PGA you calculate from the Campbell's relation, and after you calculate that relation, then you can find out that this one, number 2, is the highest, right? So that number is the highest number. So if that number is the highest, so that will be the controlling earthquake. So that we will be using that number to provide you the DHSA of that particular place. Okay, so if you know the magnitude of the fault, if you know the maximum magnitude of the fault, and if you know the distance, then this will be the thing. The distance, we always take the nearest distance in that sense, because that is where the contribution will be more. So the nearest distance from the source to the site, we always calculate. Okay?
Say this was targets. Good. So you see the peak estimation considering the 50% and material of the ground motion model site. That means it is a 0.012.
So whenever we are trying to do assessment, we take the 50% of that value. So that means if you choose that. It's a 50% time. So that means 50% time means it is basically median values. Okay, so any other question?
Sir, in previous class we learned how stochastically we can generate yes, and then find the PGA with respect to can that be used in this? Can that be used in DSC?
No. That is not the case. That is generated that if you have any point, say suppose this these things, say suppose this fault, this is the source 1. Source 1 can generate a 6.3 magnitude earthquake, right? If I am interested to get a time series of that earthquake, then I will be doing the stochastic part, right? The stochastic part will give you the magnitude. If you give the magnitude and give the distance, they will calculate the time series. They will not do anything else. Okay, so but here, what we are doing, we are calculating the peak ground acceleration or the spectral acceleration, and based on the actual happening earthquake. So that means that is where we were trying to do. Now, if you say that, okay, if I generate a since there is no other earthquake available at that site, we have not recorded anything with the 6.3 magnitude here, then we said that, okay, this is your shortest distance, this is my PGA, then you stochastically you can generate that things, but that's not the intention. The intention is this, that if you have an earthquake and if you have this much of things, then I can use that. But if you do not have anything, then of course, then we can always generate the stochastic method with that distance and the magnitude. Yes.
Thing is that TCH said that the T's functions are very different in one is a point source, then the other is a land source on it, then it shows that it doesn't matter. The only matter is this,
that where the earthquake occurs and what is the distance from the site to that. So that's the things is important, because here might be the area source, here might be the line source, here might be the point source. That doesn't matter. Matter is this, that whether that is a 6.3 and from that source zone to your nearest site location is this much of distance, then that's it. We only want that much. Okay? Make sense? Okay. So now so all are being DHS. It is the DSHA. Sorry, I'll correct it afterwards. DSH. Now, the PSHA is the probabilistic seismic hazard analysis. So probabilistic seismic hazard, unlike the DSHA, is not confined to the only one magnitude, one thing, one distance, not that. Because it assumes that earthquake can take place any point on the fault, and so we need to know from which, probabilistically we need to know what is the distance of the site from that fault where it gets ruptures, right? It is not that only one fixed point. It has a probabilistic point on which, say suppose this is a rod, this is the fault. On this fault, it could rupture at any point, and this is the site. So this distance could be any distance, right? So that, and this magnitude, whatever it will be rupture, that will be various magnitude, or a certain range of magnitude, which is characteristics of the fault. So that fault can generate from 5.0 to 7.5 magnitude earthquake. So any magnitude can be possible at any point from the site. It can get ruptures, right? So therefore, we need to accommodate that. So that will be much more scientifically much more correct in that sense, but we always need to go out with a probabilistic model. I cannot calculate a deterministic all these things, so we will be saying that it can be probably rupture from this point to this point. Of course, the rupture should not finish the fault, or should not go beyond the fault, right? Because if the fault length is this much, the rupture, if it takes place here, it should not cross the entire fault, right? So that is not, so that restriction or that constraint we should give, okay, during our formulations, right? So that's the part. Otherwise, it will be the same procedure. The procedure is that you have to calculate the source, you have to identify the source zone, and then you need to identify what are the nearest fault line or the source zone distance from the site, but that source zone distance from the site has to be done in a probabilistic manner, right? So that is what we have to do, and we need to calculate. So therefore, first part is definitely that identification or the characterization of earthquake sources. We need to first identify sources, and then we need to do the probability of potential rupture location within each source. So we have to find out what will be the probabilistically how the rupture source are distributed within the source, right? So then after you can do that, then you can calculate the ground motion based on any ground motion prediction equation if you know the distances, and then you can combine all the estimated uncertainties, because there are lot of uncertainties will be there. We need to estimate those uncertainties and combine them together. Okay, so these are the steps. So the steps are same, both the DSA and the probabilistic seismic hazard, but the DSHA has a probability either 0 or 1, because either it will do or it will not do. Okay, so we will not calculate any other in between probabilities. Okay, so DSHA is only guided by two probabilities. So whether at this point earthquake will happen or earthquake will not happen. So that is our criteria for the DSHA, but here it is not like that. So let's see, this is your site, and these are again different sources, right? So we have a magnitude, there is an uncertainty, or the magnitude, how the magnitude are distributed all along the fault, right? So that distribution we will be calculating. Okay. Next we calculate what will be the distance. So that means from the source to the site, what are the distance? So that we will be try to calculate. So this is the contribution or probabilistic contribution of the distances, and then we can take these two all together and create a probabilistic hazard map, and then we can calculate the probability of magnitude to be this much and probability of distance to be this much, then calculate the spectral hazard map of this part. So that is what is the probabilistic seismic hazard things. Okay. Now okay. So first of all, let us try with a distance, right? So how the distance can be taken care of, right? Let's see a point source. Let's see a point source, and this is the site. So this distance is RS, right? So this distance is RS. Now this RS or the epicentral distance, so if it is a point source, then if R equals to RS, then the probability is 1, and if R is not equals to RS, the probability is equals to 0. right? So that's the point source thing. Now, so that's the probability of the point source. But if it is a linear source like this, okay, if it is a linear source like this, then what will happen? Okay, let's see the linear source. If it produce the earthquake of zero rupture length, no rupture length, right? So just only earthquake produced on these things at any point, right? So then what will be the probability of these values, right? So let's see this earthquake occurs on a line source at a distance of L, and then this will be equals to L plus dl distance. Okay, so this is the length of the fault, and we are trying to calculate this one. So at a distance of L and L plus dl, we try to find out the probability, right? So and this probability, let's see, can you see the things very clearly here? Okay, yeah. So from the site, this L distance is at the R, and L plus dl is equals to R plus dr, right? So on that linear fault, these things can go from L to LR. So you can say that the probability density function for the length, if I can call it as a FLL, and the probability of density function for the rupture, if I called FRR. So that's your probability of rupture and the probability of length from one point to this one, right? That is a distance. So probability of rupture length and then probability of distance from the fault, right? So that is equals to R. So if I can say that, then FLDL, right, has to be the same as FRDR. So you can understand the dr. So R and R plus dr from L and L plus dl. So it's the probability of this one multiplied by dl has to be the same as the probability of R plus dr, because the earthquake has taken place in between these zones, right? So then that has to be the same. So then consequently, if we can do FRR equals to FL into DL dr, right? So that's your probability I can compute. Okay. Now let's see. So now the R is the epicentral distance, right? R is the epicentral distance. Now this epicentral distance is not a very good indicator or good intensity measure type of things, because that's not our objective to calculate distance from the epicenter. We are much more interested about the rupture. That means how much fault area gets ruptured. That is very important. And then if that we know, we can find out the distance from the zone. Either it is a site or might be the point site or any point, right? So therefore the rupture thing is very important, and rupture things is, we had already seen last time that the rupture is basically related with the magnitude, and there is a Wells-Copper-Smith relation which says that log 10 of rupture length equals to minus 0.74 m minus 3.55 in kilometers, with your sigma value equals to this much, right? So this is what we will be doing there. We will be doing, so instead of a, because since your FLR dr is equals to this one, so therefore we can replace FL or the rupture length in terms of the epicenter, right? So, so that's the part. So we are saying that, let's see, so this point is your, let's see, the h equals to 0, and this point h is equals to 1. So let's see, this is the unit point, and this is the site, and this site has a distance is equals to r equals to r rupture is this point. Okay, so the rupture length is starting from here and it is going up to this much, right? So that is your rupture length, and this is the midpoint of the rupture. So this is the midpoint of the rupture. So that the rupture will be within that fault zone. So the rupture cannot go beyond the fault zone. So that is what we try to do. So, and this R is the closest distance of the rupture, and so we need to calculate what is the probability of a particular value of R. Okay. R is the distance. Okay. So we are trying to say that this is the entire length of the fault, H, and this is your L rupture is here. So since the probability, I should write it, FRR, this is F suffix R, RDR, this can be calculated as, say suppose money here, FRDR equals to FLDL, right? So that is what we are trying to calculate. The probability when R is equals to R, right? So that is what it is, the probability density multiplied by dr, right? So that is your total probability. So probability R equals to R is the probability density. So this is the PDF multiplied by dr. So that's your R equals to R value, and that means same as F of L rupture by L of R rupture, because that's your this relation will show you that one, because FRDR equals to FLDL. So that your FLDL part. Okay, so and then it has to be multiplied by FHDH. So that means how much will be the length of the fault, right? Okay. Take a break.